In this lesson, we are going to talk about testing two population means when we know the standard deviation for the population. So when we're testing the difference between two means, and we know the sigma for the first population and the sigma for the second population. These are justifications for using two sample z-test. Okay, you have to meet one of these conditions. So if the population 1 and population 2 both have normal distributions, then sample size doesn't matter. However, if population 1 and population 2 are from an unknown distribution, then the sample size has to be greater than or 30 for both samples. So it has to meet one of those two criteria in order for this to work. Now, the steps are the same for the hypothesis testing. We're just going to set up our step 1 and step 2 a little bit differently. When we set up our hypothesis, in the first step, if it's a left-tailed test, then our null hypothesis is going to be mu1 minus mu2 is equal to 0. And the alternative hypothesis is going to be mu1 minus mu2 is less than 0. If it's a right-tailed test, and we have a picture that looks like this, then the null hypothesis is going to be mu1 minus mu2 is equal to 0. And the alternative hypothesis is that mu1 minus mu2 is greater than 0. And for two-tailed, we're going to have this picture. The null is going to be mu1 minus mu2 is equal to 0. And the alternative will be mu1 minus mu2 does not equal 0. So that's the case where you're just looking to see that they're different. Now, the meaning behind this, when we're looking at the alternative hypothesis, if mu1 minus mu2 is negative, that means that mu2 must be greater than mu1, because when you do subtraction and you get a negative number, that second number will be bigger than the first, and that's how you get a negative number. For the second one, for a right-tailed test, for the alternative hypothesis, the meaning would be that mu1 is greater than mu2, because if mu1 minus mu2 is greater than 0, then mu1 must be the bigger of the two. And in the two-tailed test, when we look at the alternative hypothesis, if the difference is not equal to 0, that means they're not the same. So mu1 and mu2 are not the same. If they are the same, then when I would subtract them, I would get 0. So if it's not equal to 0, then they're not the same. Now this is for step 1 when we set up the hypothesis. Now for step 2, we can use, if the justifications hold true, we can use 2 sample z-test. And then we find our p-value and we find our test statistic. Now, if we use the calculator to find our test statistic, that's perfect. We looked that up on the calculator. If you're going to use the formula for the test statistic, then your formula for the test statistic is a little bit messy, but I know some of you guys like to use the formula. Here's the formula. We have the sample mean from 1 minus the sample mean from the second sample. And then we divide by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And this is all underneath the square root. So that's to find your test statistic if you want to do it by hand. So let's look at example 1. We have a consumer group is testing camp stoves. To test the heating capacity of a stove, it measures the time required to bring 2 quarts of water from 50 degrees Fahrenheit to boiling. 2 competing models are under consideration. 10 stoves of the first model and 12 stoves of the second model are tested, and the following results are obtained. So here's the information that we get from the tests. Assume that the time required to bring water to a boil is normally distributed for each stove. Is there any difference either way between the performances of these 2 models? We're going to use a 5% level of significance. The null hypothesis is going to be mu1 minus mu2 is equal to 0. The alternative hypothesis, since we're checking to see if there's a difference either way, we're going to see if m1 minus m2 does not equal 0. And our level of significance is 0.05. Step 2. Because we have the justification that we need, it tells us in the problem that it's normally distributed. And we also know our sigmas, that's given here. We know that we can use 2 sample z-test. So I'm going to go to the calculator and find 2 sample z-test, and I'm going to find my p-value and my test statistic. And because this is that we're looking to see if there's any difference, when we put that in on the calculator, we're also going to make sure that we know that this is a two-tailed test. So pause the video for a minute, go to your calculator, put all the information in, and then check to see if you've got the same thing that I've got. So you should get that your test statistic is 1.279 and your p-value is 0.2008. So we're going to do our rejection region. And since this is a two-tailed test, I'm going to split my alpha in 2. My alpha is 0.05, which means these areas here should be 0.025 and 0.025. So on the calculator, I'm going to use my inverse norm, and I'm using inverse norm because we're using the normal distribution here. We're using the z-test. I'm going to use inverse norm to find my cutoff point, and I'm going to find that my z critical is 1.96, and then this one will be 1.96, but it's going to be negative because it's on the other side of 0. Now I'm going to look at my test statistic here. My test statistic is 1.279. So when I look at that on the graph, 1.279 is between 0 and 1.96. That's right here. So that doesn't fall in the rejection region, which means I'm going to say, do not reject the null hypothesis. For step 4, I'm going to use the p-value method. The p-value that we got on the calculator was 0.2008. Now, that is greater than 0.05, which was our alpha. When our p-value is greater than our alpha, we say, do not reject the null hypothesis. So these two match, which is good. Step 5, we have to write our conclusion. So we're going to say, since we're not rejecting the null hypothesis, there isn't enough evidence to reject it. So we're going to say, at the 0.05 level of significance, there is not enough evidence to suggest that the performance of these two stove models are different. So let's look at the second example. A teacher wishes to compare the effectiveness of two teaching methods for her students. Students are randomly divided into two groups. The first group is taught by method 1. The second group is taught by method 2. At the end of the course, a comprehensive exam is given to all students. The first group consists of 49 students and has a mean score of 74.8. The second group has 50 students and has a mean score of 81.3 points. The teacher claims that the second method will increase the mean score on the comprehensive exam. Is this claim justified at the 5% level of significance? Earlier research for the two methods indicates that coming from the first population, the standard deviation is 14, and the second population, the standard deviation is 15. All right, so for this one, we are questioning on whether or not the second group is going to have a higher grade. So when we set up our hypothesis, null hypothesis is going to be the difference between the means. We're going to start off assuming there is no difference, and then we're going to check to see if there is a difference. For the alternative hypothesis, we're going to state that mu1 minus mu2 is going to be less than 0 because we are guessing that mu2 is bigger, which means when I subtract mu1 minus mu2, it's going to be less than 0. The other way you can write it is you can just simply say that mu1 is less than mu2. Now for the second step, I know that I'm going to be able to use two sample z-test because my sample sizes are greater than 30. Where's the other one? Here it is. and because we know our population standard deviation. So that's my justification. When we put all of our information on the calculator for the 2-sample z-test, we should find that the test statistic is going to be negative 2.29 and that the p-value is going to be 0.01289. And because we're looking to see if the difference of the mu's is less than 0, this is going to be left-tailed. Okay, in step 3, we're going to use rejection region. Here's our picture. We're doing left tail, so I'm looking to see that this area under the graph is 0.05, and I'm looking for that cutoff point. Because we're using z-test, we're going to use inverse norm to figure out what that cutoff point is, and we're going to find that that cutoff point is 1.645 negative, and then here's 0 here. Now, when I look at my test statistic to check to see if it falls in the rejection region, my test statistic is negative 2.29. So that's in the rejection region. So for this one, I'm going to say reject HO. Now let's use the p-value method. For the p-value method, on the calculator, we got 0.01289 for our p-value. And that is certainly less than 0.05, which is our alpha. And when our p-value is less than 0.05, we say reject the null hypothesis. Okay, so now that we have our decision, we're going to write out our conclusion. We're doing this at the 0.05 level of significance, so I'm going to say at the 0.05 level of significance, I'm going to say there is enough evidence to suggest that the second method will increase exam scores. So overall, the steps for the hypothesis testing has not changed. It's just the way we set up the problem in the beginning, and we're